Hello! Today we're going to talk about the design of 5G millimeter wave beamforming systems. My name is Giorgia Zucchelli and I'm product manager at MathWorks for the RF mixing area. The topic of today is really close to my heart because this is where I started my career many years ago. And the topic of designing millimeter wave systems is getting a revival, driven by the need of applications such as 5G and 6G to support higher and higher data rates. And one way to support such high data rates is to use larger bandwidth or to utilize bandwidth more efficiently, often together. And one way to accommodate large bandwidth is to move to higher frequencies above 10 gigahertz or in the millimeter wave range. We see this with the opening of new bands, such as FR2, and more recently FR3, around 10 gigahertz, but also with the interest of researching sub-terahertz bandwidth. And we also see it with the usage of carrier aggregation to enhance spectrum utilization. But at these high frequencies, the losses of the channel are not negligible, which means that we need to use MIMO architecture or beamforming systems, both on the transmitter and the receive side, often using a large number of antennas, moving towards massive MIMO. Last but not least, we also see the trend of using multiple or wireless technologies to both support higher data rates and also to increase the quality of service. And we see this, for example, with the usage of both cellular and satellite networks for non-terrestrial applications. So these are the trends that we see today that drive the move towards millimeter wave frequencies. Unfortunately, however, designing millimeter wave systems is not easy. And it's not easy because there are many impairments that need to be estimated and mitigated. For example, antennas need to be packed tightly together, and this might lead to coupling. So adjacent element might leak, leading to an overall reduction of diversity. As a designer, you can decide, for example, to increase the spacing or to use defective ground structures or to put parasitic structure to reduce the effects of coupling. But all these mitigation strategies come with a cost, maybe grating lobes, maybe a larger area, costs that need to be taken into account. Similarly, at millimeter wave, power is key. It's hard to generate and transmit power, which means that losses are our enemy. And losses might be coming from impedance mismatches, dispersions in between the different elements. Especially when we operate on very large bandwidth, the characteristics of the components are not flat over frequency, which means that this needs to be mitigated using, for example, equalization algorithms or calibration algorithms. Staying on the topic of power, on the transmit side, to have maximum efficiency, we need to have a power amplifier that often operate close to saturation, which means that nonlinearity become a limiting factor, causing distortion and spectral regrowth. So typical mitigation strategy include the linearization technique, such as digital predistortion, envelope tracking, or sometimes just backing off the operating point for the power amplifier. Moving to the receiver side, as we operate on large simulation bandwidth, interfering signals might become critical. And if interfering signals have high power, that might cause desensitization on the receiver side. So typical mitigation strategies might include filtering either through filters or beamforming, gain control, or even moving towards digital receiver architectures to perform the interfering mitigation on the digital domain. Last but not least, when we stitch together transmitter and receivers, we need to take into account what happens in between, that is to say, the channel. This might have a multipath, might be affected by fading, gain losses, polarization, diversity. And to mitigate the impact of the channel and the losses, we might have to use beamforming strategies, beamforming algorithms, or using equalization and stronger diversity on the antenna side. Today we are going to explore these 5 classes of impairments one by one, and we are going to discuss how modeling and simulation help you understand the causes of the impairments and also different ways to mitigate the impairments to make sure that your transmitter and your receiver works preferably well before you build costly lab prototypes. So let's get started with our first impairment and see how we can estimate the impact of antenna coupling on beamforming algorithms. Let's start with the basics. What is antenna coupling? An intuitive way to understand it is by separating its effect in the near and in the far field. Let's assume that we have a transmitter made of 8 parallel chains feeding into an antenna array made out of 8 antennas, in this case circular patches. Because the antennas are closely spaced together, they will couple. Near-field effects can be modeled through port analysis, and in particular through scattering parameters of S parameters. S parameters represent both the impedance of the elements as well as the coupling in between the different elements. And elements that are close to each other will be more tightly coupled than elements that are farther apart. One way of thinking about it is that when I feed element 1 through the ground, part of that excitation might leak to antenna 2 and 3 and 4 and so forth in a progressively smaller value. But coupling also affects the far field radiation pattern. Think that if we excite only one antenna of the array and we do not excite all the remaining elements, the pattern of that antenna element when embedded within an array will be different from the pattern of the antenna when positioned in free space. In other words, the other antenna elements act as adjacent structure, parasitic structure that change the pattern. So you see here the embedded element of the first and the 8th antenna are different. And you might wonder, why are they different? Because they should be symmetric. Well, in this case, the feed point for each of the antennas is not placed in the center of the circular patch. Hence, there is an asymmetry on the array. Let's understand what is the impact of coupling on this specific example, an array of 8 circular patches. First, we compute the pattern of the array without coupling. How do we do that? We use the antenna toolbox in this case to compute the far field radiation pattern of a single patch located in free space. And then we use pattern superposition or the array factor to compute the pattern of the entire array. We see a big lobe pointing up at 90 degrees elevation with a directivity of 16.8 dBi. We also see several side lobes with very well-defined lobes and nulls. Then we computed the same pattern using a full-wave electromagnetic analysis of the entire array, and again we use the antenna toolbox. We see again a big lobe pointing up at 90 degrees of elevation with a directivity of 16.3 dBi. But we also see that the side lobes are a little bit larger, a little bit less defined, with nulls that don't go as deep. You might argue that the difference of half a dB in directivity is not worth the additional cost of performing a full wave electromagnetic analysis on a much larger structure than a single patch. But to really understand the impact of coupling, let's look at a different example. Let's assume that we have a desired signal coming in towards our array at 15 degrees from bore side, and that we have an interfering signal coming in at 45 degrees from bore side. So in this example, we want to steer the beam towards our desired signal, and we want to steer a null towards our interfering signal. We compute the weights with the phased array system toolbox, and then we apply the weights to our array. First, we computed the pattern of the array without coupling. Our main beam has a directivity of 16.3 dBi, and our null has a deep attenuation of 51.6 dB, which means that overall we reduce the impact of the interfering signal by almost 68 dB. Now we perform the same analysis, taking into account coupling, so with full wave electromagnetic analysis. In this case, the directivity is 16.2 dBi, only 1.1 dB of difference, but the null is 16.8 dB, which means that we attenuate our interfering signal only by 33 dB. This is a big difference and can make the difference between a receiver that works versus a receiver that does not work. Let's now see this example in practice. I'm now opening MATLAB and launching the Array Designer app. I'm going to design our array of 8 elements, our linear array of 8 elements. I'm going to use a circular patch as an antenna element. And I'm going to design it to operate at 27 gigahertz, for example. This is just an example. We design our array, which means that the elements are spaced approximately at half lambda at a given frequency. And we are now going to analyze our array with and without coupling. You can see here the spacing in between the elements, and you can see how close together these patches are. You can also see what I was describing before, how the feed point is not exactly in the center of our circle. We can now compute the 3D far field radiation pattern from our array, taking into account coupling. We can verify the directivity, as well as taking a cut at 0 degrees of elevation. And we can also visualize the antenna matrix and confirm again the main lobe as well as the null locations. We can then perform the same analysis, neglecting coupling, and we can reproduce essentially what we were saying before. We can see how the pattern is now different, and in particular how the nulls are much, much deeper. Don't be fooled here, because the scale for the two plots are slightly different without coupling and with coupling. But even just by looking at the images, you can see that there is a difference in the two scenarios, as we would expect. No big surprise here. We're going to generate a script here so that we can perform more exploration of this antenna array. So you can see here in MATLAB how we can design our microstrip circular antenna, put it in an array, and reproduce the results that we just computed with the Antenna Designer app. This is just a way to automate the analysis of your system when you want to perform multiple analyses, or, for example, more easily share these results or document these results. Good, so we analyze our structure with the full wave results, taking into account coupling on the right-hand side and without coupling on the left-hand side. And we also force the scale to be the same. So you can see how without coupling results are the nulls are much deeper. Let's now compute the weights to do the exercise that we were mentioning before. So to steer the beam towards a certain direction and a null in a different direction from which the interference signal might be coming from. To do that, I'm going to actually open up the MATLAB documentation and find an example for null steering. This is a very convenient way for me. Every time that I'm looking for a new example, I just search the documentation, and some of the shipping examples make life a lot easier. And we see here a section of code that uses the function steer_vect to steer the beam in our direction, but also to steer the null. And this allows me to point out how great MATLAB is for developing beamforming algorithms, because all these functions that are provided by the phased array system toolbox are actually white box. You can see what is the algorithm that they use, and if you like, you can modify it and enhance it with your secret recipe. So I'm going to copy the code, paste it in my script, and essentially you can see how now we apply these weights to our array. We are going to look in the direction of 15 degrees for our main beam and to 45 degrees for our null to reduce or filter out the interfering signal. We can verify with an ideal array essentially that we are indeed computing the right weights so that our calculation is correct, which is in the direction of where we were wanted to go. And now we can just apply the weights directly to our array in amplitude and phase. Without considering coupling, by simply using pattern array multiplication, the array factor or pattern multiply function, and by performing full wave electromagnetic analysis. And just like before, we force the scale of the graphs to be the same, so that indeed we can verify that our beam is steered in the right direction, but also that our null is indeed happening at 45 degrees from bore side. So here we are just adding, let me just add a cursor here. It's exactly 135 degrees, so 90 degrees plus 45 from the bore side. And you can see how without coupling, the null is much deeper compared than with coupling. So like I was saying before, this can really make a difference between a receiver that really seems to be working in presence of an interferer versus a receiver that once it gets deployed in the field will not work because it doesn't attenuate the interfering enough, sufficiently hard. Let's now look at the second class of impairments that affect millimeter wave system, frequency dispersion, and see how we can mitigate dispersion with gain calibration and equalization algorithms. But before we start, let's understand what are the possible sources of dispersion and impedance mismatches. And we use our example, the 8-channel transmitter. For example, we have a feed network that splits the input signal over the 8 channels. In this case, we have used a Wilkinson splitter, a corporate divider implemented on a PCB. This is a distributed structure, and when we analyze its S parameters through electromagnetic analysis, we see that its behavior is not flat over frequencies, not perfectly matched over frequencies, and there are possible leakages also in between the branches, by the way. A similar analysis could also be performed on the filters and other passive structures that are in general not perfectly flat and not perfectly matched at all frequency of operations. Similarly, active devices such as amplifier can be affected by dispersion. Here we see the S parameters of an amplifier, we see the gain, as well as the S11 and the S22 on the Smith chart. And this indicates that the gain is not perfectly flat, as well as the impedance is not perfectly matched. Power amplifiers are another source of dispersion, or a possible source of dispersion, because they can be affected by memory effects. What does it mean? That the output signal of the amplifier depends not only on the instantaneous value of the input signal, but also on its previous values. And this has particular impacts when we use a modulated waveform. And last but not least, we have seen that antennas are affected by dispersion, both in terms of impedance as well as pattern. When we put all these effects together, what we find out is that when we stream a signal that is modulated over a large simulation bandwidth, maybe 100 megahertz, 400 megahertz, 1 gigahertz, you name it, the behavior of the transmitter is not flat, and the impedance matching is not perfect at all frequencies. As an example, we feed our transmitter with a 4 gigahertz bandwidth white noise signal, indicated here in the spectrum analyzer with a yellow waveform. When we inspect the output, that is the blue waveform on the spectrum analyzer, we see that the output is not flat over frequency. It has notches, it has ripples. This is a factor of dispersion and impedance mismatches. Even if the transmitter is perfectly linear, the output will be distorted. Additionally, dispersion does not only change the amplitude of the output signal, but also the phase. And this can have a very important impact when using modulated waveforms, or waveforms that have complex modulations. For example, here we are seeing an OFDM signal with 100 MHz bandwidth and 124 carriers with 120 kHz spacing. On the left-hand side, you see the result of the received constellation without an equalizer. The constellation is distorted due to the dispersive effect introduced by our 8-element transmitter. If in our baseband receiver we include an automatic gain control and a static phase equalizer, we can, on the contrary, recover the constellation quite clearly. This is actually one of the reasons why reference receivers that are standard compliant are often appreciated, because they include channel equalization algorithms. Channel equalization algorithm equalize the impact of the channel, but they also equalize the impact of dispersion introduced by transmitter and receivers from TENS. Let's now look at a practical example that can help us understanding the impact of dispersion. In this case, we start from the budget analysis of the single chain that is part of our transmitter. The first element represents the Wilkinson splitter with a loss of 10 dB, representing the splitting between the input and the 8 ports. It's followed by a filter centered around 4 gigahertz, because the input center frequency is 4 gigahertz, intermediate frequency, with a relatively small attenuation at the center frequency, followed by an amplifier specified by its S parameters and its output referred IP3, followed by a modulator with a local oscillator frequency of 23 gigahertz that performs up conversion to 27 gigahertz at the output, followed by a power amplifier with its nonlinear characteristics and our circular patch antenna to transmit. On the bottom, we see the budget, and we can also plot the S parameters of the chain. So we can look S11, S22, but if you look at the gain in terms of magnitude and phase, we can really see the effect of dispersion throughout the chain. From here, we can generate a model for simulation, so moving from analysis to actually streaming a modulated signal. But before that, I want to take a little bit more of a look into the splitter. So the splitter has been designed with a RFPCB toolbox. It's implemented on a PCB substrate, on a Teflon substrate, and you can see that it's a corporate divider that splits an input signal on 8 parallel paths. Using the method of moments, we have computed these S parameters represented by the variable SW. And we can see here the S parameters of the splitter indicating the input matching condition, as well as the coupling in between the different ports, and of course the losses from the input port to the output ports. We generated the model from the budget, we copied the chains 8 times, and we connected it together with the Wilkinson splitter as well as our antenna array. We can now perform simulation using a modulated signal. The Wilkinson splitter is represented by its S parameters. We can verify the S11, the component is decently matched at the input. We can also verify the S21 that represents the insertion loss between the input and the first chain, just to make an example. And the loss is around slightly larger than minus 10 dB, which is reasonable because we are expecting a 10 log 10 of 8 loss, which is a minimum of 9 dB in ideal condition. This is the filter. We can inspect the filter centered around 4 gigahertz, both in amplitude and phase. We can inspect the S parameters of our amplifier. We can visualize, for example, on the Smith chart, both the S11 and the S22 and see how the matching condition change throughout the frequencies over which the amplifier is defined. This also allows me to point out how great MATLAB and the Ref Toolbox are for managing S parameters. Importing, visualizing, cascading, de-embedding, transforming, you name it, a Ref Toolbox provides you with the function to do it. But back to our design. We also have phase shifters that introduce dispersion in this case, which is interesting. When we run the simulation, in this case, we combine all the effects of dispersion and impedance mismatches across all the elements and all the chains. Additionally, we also take into account coupling introduced by the splitter and the antenna array. Here we use a 4 gigahertz white noise signal at the input, indicated in yellow, and in blue we probe the output of our transmitter, the output of the antenna, and we clearly see the effects of dispersion on the amplitude with the different notches and the different gain. This is very useful because it means that not only we have statically analyzed our chain, but we can actually simulate it, which means that now we can stream modulated signals through the chain and take into account the effects of dispersion. Let's talk about the third class of impairments for today that primarily affects transmitters, that is to say the nonlinearity of power amplifiers, and see how we can use digital predistortion to mitigate this phenomena. In power amplifiers, the output power of the signal increases linearly as a function of the power of the input signal and proportionally to the gain until the amplifiers enters in compression. At that point, the output power saturates, and this means that we have a spectral regrowth and distortion, which are in general undesirable because they decrease the quality of the transmitted signal. At the same time, operating in compression is desirable because it maximizes efficiency. So we have two contrasting requirements. So one way to keep the characteristics of the amplifier as linear as possible and the quality of the signal high is to implement digital predistortion. Digital predistortion implements the opposite characteristics of the amplifier so that when we cascade the two, the overall behavior is linear. This is the theory and is relatively easy to understand. The practice is a little bit more complicated. This is because the power amplifier is affected by memory, which means that the output of the power amplifier at a specific point in time not only depends on the input at that specific instant, but also on the previous values of the input signal. And this has large consequences when you deal with modulated signals. Second, power amplifiers operate in the RF domain. Digital predistortion operates in the baseband domain, which means that we need to take into account up conversion, down conversion, and timing effects that might cause instability when closing the feedback loop. Last, there is an effect of antenna loading that can be extremely complicated when you have transmitters with multiple antennas, like we have seen. To study and to develop digital predistortion algorithm, the first thing that is needed is a model of the power amplifier. In a RF block set, you find a generalized memory polynomial for the power amplifier and a fitting procedure that can be applied to your measured data. The generalized memory polynomial allows to model the memory by looking back to a certain number of samples. I and Q samples in the time domain are what are used to identify the model, as well as models nonlinearity by using a certain number of orders in the polynomial series. Like I was saying before, using I and Q time domain wideband measurement data, you can extract a matrix of complex values that represents the model of the power amplifier. And the model actually reproduces fairly well the behavior of the power amplifier, given that the waveform has a realistic dynamic range, peak to average power ratio, and bandwidth. By the way, in RF block set, you also find an extension of the generalized memory polynomial model that also includes lead and lag terms for which is provided a causal implementation. Now, let's say that we have a model of a power amplifier that we have identified using this procedure. There are many ways in which you can linearize a transmitter with multiple chains. So you might have to perform an architectural exploration among the different options. For example, you could use an over-the-air approach in which the observer path is based on the information provided by an antenna placed in the near field compared to the transmit array. An equivalent implementation positions the observer antenna in the far field, always feeding a single digital I and Q chain. Another on-chip or on-board architecture could consist in probing the output of the power amplifier of one or a limited subset of the power amplifiers of the MIMO transmitter, under the assumption that all the power amplifiers are essentially very similar or behave in a similar way. Another option, more complex, is to combine all the outputs of the power amplifiers of the MIMO transmitter with the channel emulation block that provides the information to the observer path for the digital predistortion algorithm. Or alternative, we could think of a structure that is time shared with a switch that toggles in between the different outputs of the power amplifiers. Or these are architectural choices that you can explore with the use of a model of the power amplifiers plus a simulation environment where you can model all the additional control logic, digital signal processing algorithm, as well as low power electronics. But to test a digital predistortion algorithm and to verify if it works, you need to use modulated waveforms. We left before with a white noise signal to test the dispersion. Now we're going to close this gap and use a fully standard compliant 3GPP waveform to test our RF transmitter. We can use any arbitrary waveform for FR2, FR1, test model 1.1 or 3.1. Different options are possible depending on the type of system that you are keen to test. And by the way, if you don't use a 5G, but you use wireless LAN or satellite communication waveforms such as DVB-S2, other options are also possible in MATLAB. This gives me the opportunity to mention how great MATLAB is for waveform generation, custom or standard. And if you wonder where you can start, the wireless waveform generation app is a great place. Here you find the standard signals, custom signal, 5G, LTE, wireless LAN, even radar signals. And you can customize the waveform generation and verify its spectrum and its resource grid as you go along. But back to our example. Here we generate the waveform, we stream it through our RF receiver, and then at the output we measure the standard compliant ACLR as well as EVM. We performed the simulation twice with and without digital predistortion, and we verified that the DPD algorithm can indeed improve both the EVM as well as the CPR. So what we have here is MATLAB script. First of all, we set up some global variables like the input frequency, the output frequency, the local oscillator frequency, and we load the designs of the antenna that we performed before. Then we generate a 3GPP waveform. We can use any standard channel. In this case, we use a test model 3.1 with 100 megahertz of bandwidth and frequency division multiplexing. We generate the waveform, it's fairly straightforward, and then we scale it. We scale the input power so that we know that the input signal will be within the dynamic range of our transmitter. We also visualize here the input power as well as the peak to average power ratio. And then we stream our input waveform through an object that is called BFICTX. This BFICTX is an RF system, is nothing else but a wrapper of a Simulink model. A Simulink model that is in this case called BFIC_TX_ model. And you see here the properties of the input frequency and the output frequency of this model for the circuit envelope simulation. If we open up the model behind the scene, when we run this command, essentially there is a Simulink model that represents our transmitter plus the digital predistortion algorithm. So you see the input signal from the input port to the splitter through the chain to the antenna array, the theta and phi polarization component, the output we probe the theta component, you have a spectrum analyzer. We sense the output with a far field antenna. In this case, it's just a simple dipole. We feedback with the digital predistortion algorithm and the switch that we can toggle on and off to enable or disable the linearization of our transmitter. Talking about digital predistortion gives me the opportunity to mention how you can generate C and especially synthesizable HDL code for the digital predistortion algorithm, including actually also the coefficient estimations. This is a great deal because this allows you to rapidly prototype your algorithm and test them actually over the air. But now back to our model. So when we run the simulation, you can see here from our MATLAB test bench, we just pass the input waveform to our model, and we get the output waveform at the output. As we run the simulation, for example, we can inspect the spectrum analyzer to see the spectrum of the signal as it gets streamed through our transmitter. And just as a reminder, we perform circuit envelope simulation, so multi-carrier simulation, where essentially we take into account not only of the dispersion and memory effects, but impedance mismatches, but also the nonlinear effects. We fast forward now. Let's load the simulation results. So you can see in yellow the input waveform, in blue the output waveform. We can now measure the ACLR for a 100 megahertz bandwidth signal. Let's look at the two adjacent channels spaced just 5 megahertz away from our reference channel. And you can see here that due to the nonlinearity of our transmitter, the ACLR is -38, -37 dBc. You also see how the spectrum is asymmetrical due to the memory effect introduced by our power amplifier. We can measure the EVM, again, using the standard compliant 3GPP functions. We see here the constellation, taking into account the nonlinearity and some of the dispersion introduced by our transmitter. We can now toggle our switch, so enable digital predistortion, rerun the simulation. Here we're going to fast forward and just load the results that we previously computed. We can see, compare the spectrum of our output without digital predistortion, with the -37 dBc of ACLR, and with digital predistortion. We can see how we improve the ACLR to -45 dBc, which is a significant amount. We can also measure the EVM using the same function that we used before and see how the constellation is now much, much clearer, and how the digital predistortion effectively compensated for the nonlinearity, but also for some of the dispersion introduced by our transmitter. As we are talking about amplifiers and nonlinearity in general, I'd be remiss if I wouldn't put transmitter emission in a slightly wider context. So let's make a fun experiment. Still working on our 8-channel transmitter, let's focus on the INQ modulator. So we have a starting input frequency of 4 gigahertz, a local oscillator of 23 gigahertz, and the modulator performs a conversion at 27 gigahertz. And by the way, the local oscillator might be affected by phase noise with different distributions. Let's also assume that we steer the beam at 15 degrees from bore side. With our simulation model, one can verify what is the effective isotropic radiated power at the given direction, 15 degrees, as well as at the given frequency of 27 gigahertz. As a fun experiment, let's now assume that our modulator is affected by a low leakage. That is to say, part of the power of the local oscillator leaks to the RF port. This means that we are actually transmitting a signal at 23 gigahertz of output frequency. And we can actually verify what is the EIRP and the radiated power at the output emission frequency. So in this case, due, for example, to the dispersion and non-ideality of the chain, what might happen is that the beam points in a completely different direction or unexpected direction. So with these simulation models, you can really take into account spur and spectral emissions also outside the frequency of interest, thanks to the multi-carrier circuit envelope simulation. So let's say this example in practice. I'm going back to the Simulink model as we left it, our BFI-CTX. And I'm going to browse down and plot the pattern, in this case, at the output frequency of 27 gigahertz. Here we are probing the instantaneous voltages at the terminals of the antenna and use these instantaneous voltages essentially to feed the electromagnetic solver and look at the pattern as it is. The good news is that we are steering the beam in the desired direction with the desired EIRP. Let's stop the simulation and change the observation frequency. So rather than looking at 23 27 gigahertz. I'm now going to plot the pattern at 23 gigahertz. So I'm probing the instantaneous voltages at 23 gigahertz. This is the characteristics of our modulator with the finite and low isolation as well as the phase noise. We can also plot the phase noise characteristics just to show that there is something more than just a SW tone coming out at 23 gigahertz, just to make an example. And when we plot, we can actually verify where the beam is pointing and what the EIRP is as well. This is interesting because you will see all dispersive effects as well, the combination of dispersion and non-linearity interacting on your transmitter. And different antennas will have different behaviors, so it's or different frequencies, and the accumulation as well of the nonlinearity will impact your transmitter differently. And here also you verify the actual effective isotropic radiated power. From undesired emissions on the transmitter, let's move to the reciprocal problem and estimate the impact of interfering signals on wideband receivers. This is the fourth class of impairments that we will see today that affects millimeter wave systems. Interfering signals are particularly dangerous for wideband receivers because they might cause saturation and desensitization. In particular, they might raise the noise floor and reduce the signal-to-noise ratio to the point that your receiver will not be able to recover the desired information. Interfering signals sometimes can be removed either by filtering in the frequency domain if they are out of band, or maybe by null steering. This is one degree of freedom that is added by using arrays of antennas, phased array systems, where essentially we can steer a null towards the direction of arrival of an interfering signal and essentially reduce its impact. So let's consider an example where we have a 400 MHz 3GPP FR2 test model 3.1 signal coming in at 27 GHz and at 60 degrees with an input power of minus 70 dBm as an input to our receiver. And we also consider an additional interfering signal that is a modulated waveform with 100 MHz of bandwidth, so a different characteristic, coming in at 19 GHz and at 40 degrees for the array with the same input power, minus 70 dBm. Here we chose both the frequency and the angle to represent a worst-case scenario. Because we steer the beam at 60 degrees, in this case, due to the dispersion or to the dispersive effect in the receiver, when we look at the beam at 19 GHz, it actually gets steered towards 40 degrees. So we have maximum directivity in this direction, which is very undesired. It's sort of a worst-case analysis. Similarly, 19 GHz is the image frequency for our demodulator. So when 19 GHz mixes with a local oscillator of 23 GHz, it also downconverts to 4 GHz, that is our intermediate frequency. In other words, the interferer signal gets downconverted straight on top of our desired signal. Of course, the demodulator has an image rejection filter, but because the receiver is wideband, the rejection of the filter is finite, which means that part of the interfering signal will still map onto the desired bandwidth. The result is unfortunately that the resulting EVM is degraded from 3.6% to 4.2% in presence of the interferer. And when we look at the EVM per subcarrier, we can really see the folding of the 100 MHz of FDM signal straight in the middle of our receiver bandwidth. So we go back to another MATLAB test bench, essentially where we again have global variables, where we load our design of the antenna, as well as the splitter. We also generate our 3GPP waveform, just like we did before, and scale the input power. This is our desired signal, and feed it through another system, an RF system that in this case is called RF-RX. So here is our RF system where we see on the top branch the 3GPP waveform coming in to our antenna array, and on the bottom side the OFDM signal coming in. The antenna array has two input frequency and two direction of arrival, one for the desired signal and one for the interfering signal. If you look at our demodulator, we can see that we insert an image rejection filter. Is a simple Butterworth filter of third order with very large bandwidth, so its rejection at 19 GHz will be limited. This is just an example. On the left-hand side, we see the spectrum of the interfering signal, and on the right-hand side, we see the spectrum of the received signal, the combination of the desired plus interfering signal. And because the interfering signal is essentially slower in power than the desired signal, we can't really see much from the spectrum. We complete the simulation, fast forward, we look again at measure the output power, we can look at the spectrum, but it's more interesting to look at the EVM measured using the standard compliant functions that allows us to visualize how the EVM for those subcarriers that are right in the middle is actually degraded. And this is really the effect of the interfering signal that falls in the middle of our received bandwidth. Let's now cover the fifth and last class of impairments for today and talk about RF propagation. In particular, we will discuss how to use ray tracing to model a channel and stitch together a transmitter and a receiver. Ray tracing is a very interesting technique because it allows us to model multiple paths in between the different antennas on the transmitter on the received side. This can be particularly important at mmWave, where line of sight is essential for communication, and when you have, for example, complex scenarios such as in urban configuration where you have multiple buildings with lots of surfaces and lots of bouncing rays. So ray tracing allows us to model multiple radiated and incident direction, different path loss, as well as phase rotation that occurs at all these levels. When we combine ray tracing together with an accurate electromagnetic model of the antenna arrays, then we can also take into account antenna coupling and frequency dependency. So when we use a channel together with our transceiver, we can really perform an end-to-end simulation spanning multiple domains, from the signal flow to circuit envelope multi-carrier simulation for the RF front end, to EM analysis for the antenna arrays, to ray tracing for the channel itself. So let's see an example in practice. So in this case, I'm going to start from the MATLAB documentation. So I'm going to search here for channel, and the first hit is going to lead me to the channel block in the circuit envelope library. Fairly straightforward. I open up the documentation of the channel block, and I see immediately a script that essentially I use to model a scenario. Center frequency 27 GHz, base station position and UE position are given in latitude and longitude. And you can see them here that they are inserted in a scenario with buildings actually located in Hong Kong. For the transmitter and receiver, we just use a simple dipole in this case and a propagation model that uses ray tracing with two bounces. This is the model, it's fairly straightforward. You see that it uses a certain location for the transmitter and for the receiver, what we just defined in terms of latitude and longitude. And now we can also visualize them with all the rays in between them. And we can see, actually estimate the distance as well as the path loss, as well as the direction of arrival and departure, both from the transmitter and the receiver, which is very interesting. So in this case, we are good because there is direct line of sight. We can now perform the simulation and look at the budget. But let's look at a slightly more interesting scenario where instead of using a single antenna, we actually use our antenna array, 8 circular patches. So I'm going to use this array both on the transmitter and the receive side. Additionally, I'm going to move the UE, so I'm going to move the receiver side in such a way that we will not have any more direct line of sight. We keep a propagation model with 2 reflections, and we now open our RF model that has 8 branches. So we have again the transmit and the receive with the channel that connects them. We see that we receive -69 dBm of power And we can actually verify the link on the scenario situation. So in this case, like anticipated, we don't have a line of sight. And it's interesting because if you select one of the rays, we can see what is the angle of departure and the angle of arrival, again, for the transmit and the receive. Well, let's stop the simulation for a second, and let's now beamform at the transmit and the receive side in such a way that we steer the beam towards the desired direction, and we can actually increase the received power. This is a simple example that allows you to connect a ray tracing channel to a complex transmitter and a complex receiver, and eventually also perform end-to-end simulation. Before I wrap up with the conclusion, I would also like to point out that ray tracing is not the only way to model a channel, and that in MATLAB you find many other channels, statistical and standard compliant, if you would like to use a different representation for the propagation effects. Summarizing, today we have seen a lot. We started with antenna arrays and saw the impact of coupling on beamforming algorithms. We have seen the impact of dispersion and frequency dependency over and over again over wideband modulated signals. We talked about amplifiers nonlinearity and saw how digital predistortion can help in mitigating it. Then we jumped into receivers and saw the impact of interfering signals and how they can degrade the quality of the received signal. And last, we saw how to can model RF propagation effects using ray tracing. The bottom line is that designing 5G millimeter wave systems is complex. The physics are just complex. But using modeling and simulation can make it significantly easier. Because with models, you can anticipate and understand what really matters. Is it antenna coupling? Is it dispersion? Is it nonlinearity? What is the impact on my end-to-end link? With models and simulation, you can scale up the system beyond simple calculation and beyond CW measurement. We have used modulated waveforms over a large bandwidth that give a much higher degree of accuracy in your system model. And you can validate results at every step. You can isolate impairments one by one. And with this, you can really gain true insights into your system architecture and your algorithms before and during building complex lab prototypes. I thank you very much for your attention. I hope that this was useful for you. Please follow up with MathWorks and look at all the resources that we have online. Thank you.